Okay, we are in Generalized Linear Models, examples in R, and there is great news today. It is the last question of Chapter 3. So that's exciting. We get to move on to some interesting things next, but we need to answer this one first. Okay, so we have a data set called butterfat. And what butterfat is doing is it's looking at 5 different breeds of cattle and then looking at the butterfat content of their milk for 2 different age groups, older than 4 years and 2 years. Okay, and we're asked to do some things with this. All right. So the first thing you need to do is to install and load the GLM's data package. You need to call up the butterfat data, and here I'm just calling it D, and we can get a look at what it looks like. We can see what it looks like here, and so you see that we have butterfat and breed and age. Okay, and well, I guess that we're told that there's 5 different breeds of cattle here, and just this little preview, we just see a few, one of them. Okay, so the first thing that we're supposed to do is to plot percent butterfat against the breed and age, discuss any features that are apparent. So I went a little bit overboard here. So instead of making 2 plots, I'm making 1 plot, this box and whiskers plot. And so we have the different breeds and ages across the x-axis, and each age group for each breed is coupled up. So, and those are denoted by the 2 different colors. So you can compare within the breed, what the ages, the differences between the ages here. Okay, so we're also asked to comment on any features. Generally, I don't like these kinds of questions because it kind of depends on like what you know about the subject matter and what's important and da 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 da. You need a lens through which to view anything. So here, it's a little bit tough, but I mean, maybe we could say something like, across age groups, or especially across species, there seems to be a little bit more spread in some species than others, and often more spread in the younger animals than the older animals. I might say that I don't know anything about dairy cows, but that seems a little bit surprising because the age group for the older animals is much broader, 4 to 10 years old instead of 0 to 2. But perhaps that just reflects, as these cows mature or something like that, that they're maturing at different rates, and so it's more variable. So I'm not sure. So, okay. But it turns out that the thing that we are focused on in this question is kind of this heteroscedicity, and so we're going to try to remedy it with some transformations. And so it says to use various transformations to make the variance of the response approximately constant. Okay. Which transformation appears appropriate, and does the boxcox transformation help the decision? Okay, so the book just has a itty-bitty bit about using the boxcox command in R, so we'll use that here. So yeah, I guess let's get into that. The only transformation that we're going to use is the one suggested by the boxcox transformation. It's kind of the function of this transformation to pick out the transformation that is most apt to conform, to transform your data so that it conforms to the to be approximately normal. So so to do that, we need to load the mass package. Okay, and then you just go through some formalisms here. So first we just we have to look at butterfat. Okay, on this part here, I'm a little bit I'm a little bit uncertain as to whether or not we need to regress it on the other variables or not. The way that I read this question, it just asks, how do we make, well, the way that I read it, I'm not sure, but I am just regressing it on the intercept here. Okay. On the fly, I think that maybe I was doing that just to see what would happen here. So I'm going to change this on the fly here. How about that? Age and breed. Okay. So what the boxcox thing is going to do is it's going to go through and it's going to look for certain values to kind of scale, I guess we want to say, to scale our data that makes it conform to the normal distribution. So this is in section 3.9.3, kind of roughly how it works, okay? And then it's going to pick the best lambda, and then we're going to apply the transform to our butterfat data using the best lambda, the lambda that does the best job at making our data appear normal. Okay, so that's all that's going on here. Okay, and so it's telling us that the best lambda is negative 1.4. We don't, it doesn't really mean too much to us right here because we're not going to hard code that into anything. Okay, but let's look at what happens to our data, our transform data here. Okay, so this is the same plot, but now we have the transform data. Okay, and here, I don't know if I see much difference, but that's really not the best way to see if we've made a difference in the variance. What we should do is apply the white test, which we did in the previous problem, question 3.29. So I won't go over it here, but you should definitely see that. Okay, but roughly what we do is we're fitting, we're fitting our two models. Okay, one for butterfat, one for the transformed. And then we regress in each case. We regress the residuals, the squared residuals, okay, on the fitted values. And here I'm using a polynomial, so the fitted values plus fitted values squared, just because, kind of imperfect variance for a normal linear model can have a lot of different shapes and forms, and so we capture more of those bad shapes and forms, by regressing on more things. Okay, and then, I guess the way that I'm assessing whether or not it gets better is I'm just looking at the p-values for both of them. And now a low p-value means that there is heteroscedasticity, and a high p-value means that there's not. And sure enough, the first model, where we did not transform anything, was very much heteroscedastic, but not for the transformed model. So it looks like our transformation did something positive here. And then for the last one, what we've done in basically every question in this chapter is fit an appropriate linear regression model and interpret diagnostics. Okay, well, we fit an appropriate model right here, m.bc. So we'll just look at the diagnostics here. And again, we can go into more depth here, and we do in some of the other problems, but a good first step is to just use the plot function. Okay. And here it seems that that our model is doing a fairly good job of of capturing the data, right? So so we see that the residuals are more or less homogeneous across the different fitted values. The QQ plot is the data is doing a pretty good job of clinging to that QQ diagonal there. And it doesn't seem that we have any offending values that are particularly high in their influence over the fit of the model. So, okay, we'll call that good.